decimal to hexadecimal conversion, so this is also similar in nature. So here we have to divide by 16, as you can understand by this time. So this base conversion, so we'll be dividing it by 16. So divide by 16 and keep track of the remainder. So 1, 2, 3, 4 to the base 10 converting to hexadecimal. So only thing is that division becomes a bit complex. So divide by 16, so remainder is 2. Then divide by 16, remainder is 13, and 13, the corresponding hexadecimal symbol is D. Okay, so 13 is basically D. So this is the integer value, and this is the hexadecimal symbol corresponding to that. And then this 4 divided by 16, remainder is 4. So the number that you get is 4D2. So this 4D2, so this is the number corresponding to this. So this way we can convert by decimal number to different hexadecimal numbers. Now the other way, binary to octal. Okay, so how can we do this thing? As I already said, the one possibility is that this binary number you convert to decimal, and from this decimal you go to octal. So that is one avenue, but you can say that is 2 conversions will be necessary in the process, but that is not required. So you can do it directly. So you can group bits in 3s starting on the right and convert to octal digits. So we'll explain it with an example. Suppose this is the binary number that we have, and it does not, so I want to get the corresponding octal number. So what is done? So I make groups of 3 starting from the right side. So you must keep in mind, so you should not start from the left side. So you should start from the right side, okay? Then this first 3 bits 1, 1, 1, they form the first group. Then this 0, 1, 0 form the next group. Then this 1, 1, 0 from the third group, and here I don't have 3 bits, so you can safely assume that we have got these bits as 0 zeros. 2 zeros are there. So as a because I can always assume that there are 2 zeros at this point, and because they will not contribute anything to the number, so I can do that. So that way I can have this. So now you convert the bits, the 3-bit patterns into corresponding octal numbers. So this 1, 1, 1 is 7, 0, 1, 0 is 2, 0, 1, 1 is 3, and 1, 0, 0, 0, 1 is 1, and the corresponding number becomes this 1327. So this is the corresponding number. So if you are going for this binary to hexadecimal conversion, so here also the same thing. So but now the grouping that we will do will be in terms of 4 bits. So we will be grouped in terms of 4 bits starting from the right side. And then the groups, the bit pattern group that we have, so they will be converted to hexadecimal digits. So here, so we are grouping in terms of 4 bits from the right. So this 1, 1, 0, 1, they form the first group. Then this 1, 1, 0, 1 form the next group. And then I have got only 2 bits left, 0 and 1. So 0, 1, and as I did in the previous case, so you can safely assume that we have got zeros here, and those zeros are brought here. Okay, so we can have this 0, 0, 1, 0. So ultimately the pattern becomes 2BB, and this 2BB is the hexadecimal number corresponding to the decimal number, the binary number that we have. Okay. So then how to convert octal number to hexadecimal numbers? So it says that you can use a binary number as the intermediary. So we take, what we do is we convert the octal number to binary number first, and from the binary number we convert to hexadecimal number. Like say this is an octal number 1076 to the base 8. What is the value in the hexadecimal number? So first this 1076, so since this is an octal number, so individual digits I can convert it into 3-bit patterns and getting the corresponding binary bits 001, 000, 111, 110, and now I will be grouping them in terms of 4 bits, okay, from the right side. So this so you see that this part, so this portion up to this much, so it is taken as one group, then this part is taken as another group, this part is taken as another group, and then this part is taken as another group. And again, for making it 4, so the 2 extra zeros have been added, okay, at the beginning to make it a group of 4. And then you convert it into the corresponding hexadecimal number. So this 1110, so this is 14. So 14 in hexadecimal number system is E, so that is E. Similarly, this is 0011, that is 3. So that is in hexadecimal also this is 3, and 0010, that is 2. So in hexadecimal system that is 2. So you can do this conversion, and accordingly you get this 1076 in hexadecimal in octal number system is equivalent to 23E in the hexadecimal number system. Now hexadecimal to octal, so this also you can guess what are we trying to do, what we will be doing. So we will be converting hexadecimal to binary, and from binary we will be converting into octal. So we will be following this avenue. Okay, so let us see how it is done using binary as intermediary. So suppose we have got this hexadecimal number 1F0C to the base 16, and we want to convert into corresponding octal number. So this first of all this 1F0C, so that we write down the corresponding binary representation, and we know that straight away we can convert these individual digits to binary 4-bit binary patterns, and then that gives us the binary representation of this number. Now after that, since I am trying to go to octal, so I have to make them groups of 3. So I make groups of 3 from the right. So this 001, that is there. Next group is 100. Next group is again 001. Next group is 111, and the last group is 100. So 3 extra zeros have been padded so that we can make it. We can get a 4-bit pattern here. So that way, the number that we get in the octal number system is 17414 in the octal number system. So this way we can convert very easily between this octal and hexadecimal number systems using this binary number system as the intermediary. Okay. So otherwise we have to convert to decimal, and then by multiplying by powers of 8, and or dividing by power, after that dividing by powers of 16 if we are trying for octal to hexadecimal conversion. Or hexadecimal to octal conversion, you have to convert to decimal by multiplying by powers of 16, and then from that decimal number to octal by dividing by powers of 8. Can do a very simple exercise like we have got a numbers and how to what the values will be in different number systems. So this is the answer. So 33 in binary number system, so this will be 1000. Actually, whenever you are doing these operations, this binary number system, so there can be an easier way of doing this conversion. So you need not always go on dividing by 8. Okay, so we'll look into a technique, and that will make it simple. Okay. So let us say that if we look into these individual digits of a binary number system, so the first, so if this is if suppose this is a 4-bit number, for example, 4-bit binary number. Okay. So what is the contribution of the first number? So that is 2 to the power 0 equal to 1. Contribution of the next digit is 2 to the power 1, that is equal to 2. This is 2 to the power 2 equal to 4, and this is 2 to the power 3 equal to 8. So any number that you are representing, so they will be summing up the values of this 8, 4, 2 and 1. So if I take the number say 1, 1, 0, 1, so the number is 8 plus 4 plus 1, so that is 30. So now if I ask you the question in the other direction, I tell you what is the representation of 13 in the binary number system, and you have in your mind this particular scale, okay, that on this scale I have got these values. So this is 8, this is 4, this is 2, this is 1, these are the weights. So what you do from 13, so since the most significant value of the weight is 8, so this has to be given to reach 13. So from 13 I have given 8. So I am left with 4. I am left with 5. Next value is 4. So I have to take it because I need to reach 5. So I have to take it. So this one also I take. So what is, now I am left with 1. Fine. But the next weight is 2. So I cannot take this. So I put a 0 here. And the next one I am still left with 1. So I take a 1 here. So you see that if I just remember this particular scale, then I can just put them ones and zeros to convert it into the binary number system. So any arbitrary number, let us take say 136. First of all, we have to see how many bit representation will be required for 136. See, if I have got n bit, so if I have got n bit binary number system, then it can represent numbers in the range of 0 to 2 to the power n minus 1. So n bit binary numbers, for example, if you take n equal to 4, so you can represent numbers from 0 to 15. If you take n equal to 3, then you can represent the numbers 0 to 7. If you take n equal to 5, you can represent numbers from 0 to 31. So for 136, what will be the value of n? So value of n will be the next power of 2 after 136. Okay, so the next power of 2 is 256, that is n equal to 8. So I will need an 8-bit number system to represent 136. So in a 8-bit number system, what happens to the values? Like I have got the first value is, if I write from the LSB side, first is 1, next is 2. So I am just writing these positions that we have written here, so 1, 2, 4, 8 like that. So if you are writing like this, so 1, 2, 4, then 8, then 16, 32, 64, 128, 256. This is that 8-bit range that we have. Now for the number 136, we do not need this 256 bit. So this is 0. Fine. Now 128 I need, because I want to represent 136. So 128 I need. So after I have taken 128, I am left with only 8. Okay. So 64 I don't take 32, I don't take 16. I have to take 8. After that, value has become 0. So none of these bits are necessary. So 136 is actually represented as the bit pattern 0 1 0 0 0 1 0 0 0. Okay. So this so 8-bit so I'm sorry, this 120 after this this 256 will not come here, because I am going up to n equal to 8. So this is 1, 2, 3, 4, 5, 6, 7, 8. So up to this much will be necessary. So this will be up to 128 will be necessary, and in that 128, so this one for representing 136, 128 will be necessary. So this 0 is also not there. This 136 will be necessary. After that, I will be taking this only 8 will be left. So this 64, 32, 16. So they will not be necessary. Only this 8 will be necessary again. Okay. So let us take another example. Let us take another example. Say 175. Okay. So for 175, again the same thing, that the next power is 256. So that means I need an 8-bit representation. So 8-bit if I take, so 1, 2, 4, 8, 16, 32, 64, 128. So these are the 8-bit weights. Okay. So for 175, I will need this 128. After I have taken 128, so 175 minus 128, so that gives me 47. So 47 more has to be represented. So I cannot take this 64, so that is 0. I have to take this 32. So if you subtract 32, so you are left with 15. So I don't take this 16. I take this 8. So minus 8. So left with 7. So I have to take this 4. Minus 4. I am left with 3. So I take this 2. Minus 2. I am left with 1. I take this 1. Minus 1. Left with 0. So the 170, the value 175 in the binary number system will be given by 10101111. Okay, so you can check the corresponding decimal value to be equal to 175. So this way we don't need to always do that division by 2 and all. So if we just remember these powers of 2, and we can just go on assigning, you can go on taking those positions by turning on the corresponding bits to 1. Okay, so here also is 33. So 33 means I will be requiring say 6-bit representation, and in that 6-bit representation, so this is this value is 1, so this is 2, this is 4, this is 8, this is 16, this is 32. So 32 plus 1, 33. 117, so I will need 7-bit representation, because 2 to the power 7 is 128, and then this is again the thing 1, 2, 4, 8, 16, 32, 64. So say 64 plus 32 is 96, plus 16 is 112, plus 4 116, plus 1 117. So that gives us 170. So this way I can do the conversion. And once you have converted into binary, then octal and hexadecimal conversions are very simple, because for octal conversion what I need to do is I have to make groups of 3. So I make a group of 3 here, I make another group of 3 here. So the first group is 1 and the second group is 4. For hexadecimal, I make a group of 4 and then I make a group of 4 like this. So that way it is 21. Okay. Similarly here I make groups of 3. So this is one group, this is another group, and this is another group. So I get 165 in octal. And if we are taking hexadecimal, then this is one group and this is another group. So the first group is 1110. So 0111. So that is 7, and the next one is 0101. That is 5. So this way you can you can very easily do a conversion from decimal to binary by taking help of that number scale, that powers of 2 scale, and then from there you can go to octal and hexadecimal numbers very easily. You don't need to do those multiplication, divisions and all. Okay. So next common powers. So these are the different names that are given. Base 10. So 10 power minus 12 is called pico. 10 power minus 9 is called nano. Minus 6 is micro. So these are the standard thing. Up to 10 power 12 is tera. So in representation we represent them by small p, small n, then micro, then small m, small k for kilo, then capital M for mega, capital G for giga, capital T for tera. So this is common powers of base 10, and the corresponding values are like this. Okay, so 10 power minus 12 is this one. So this is known to us. Okay, so if you base 2, so we have got 2 power 10, 2 power 20, 2 power 30. They are called kilo, mega and giga. So those are the corresponding symbols, and the values are 1024, then this one and this one, 2 power 20, 2 power 30, like that. Very big numbers. What is the value of kilo, mega and giga? So these are the values actually. In computing, so particularly with respect to memory, so we'll be using base 2 interpretation. So in case of decimal number system, so kilo means 1000, but in case of binary number system, so the kilo is 1024. And in computer systems or in digital processors, so whenever we are talking with respect to memory, so we'll be talking about kilo as 1024, and then mega is 10485, so there's 2 power 20, 2 power 30 like that. They are not the powers of 10. Okay, so some common rules, like say for common basis we can add the powers. Like if you are multiplying two numbers a to the base a to the power b and a to the power c, then we can add the powers. So we can say a to the power b plus c. So 2 power 6 into 2 power 10 is 2 power 16, or 65536, or say 2 power 6 into 2 power 10 is 64 to the power 10. So I can either convert it in this, and then we can say it is 64k. So either we can visualize it like this, 65536, or we take it to the power of 2. Okay, so we say that it is 64k, whereas the actual value is 65536. So when you are adding binary numbers to add to 1 bit values, so this is the rule. So both the bits are 0, a plus b, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 2. So which will be requiring 2 bits for representing it, so that is 10. So that is 2. So if you are adding two n bit values, so you have to add individual bits and propagate the carries. Just like in decimal addition, so if we are propagating the carries, so here also the same thing. Like in decimal system, so if we are adding say 45 and 96, so what are we doing? So 6 plus 5 is 11, so we write 1 here, and this 1 carry is taken to the next position, and then 9 plus 4 plus 1, so that is 14, so 4 is written here and 1 is taken as a carry, and then that carry appears at this point. So that way we can have the same thing in case of binary number system as well. So we can say that we can add individual bits and propagate the carries. So here 1 plus 1 is 0 and carry is propagated, then 1 plus 0 is 1, so there is no carry. Then 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0, and this 1 is propagated, so this is 1. So this gives us the number 46. So that is, you can just check it that this is really 46. Multiplication. So we can multiply decimal numbers, so like this. So this is the way we do multiply. So first we multiply by the first digit, then do a shifting, multiply by the second digit, then do another shifting, multiply by the first digit, and then we just sum all these partial results, okay, to get the overall multiplication value. So here also in case of binary number system, so the rule is like this: 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, and 1 into 1 is 1. And then if we are doing some multi-bit multiplication, then we have to do the similar rules that we do for the decimal one. So first this is multiplied by 1. So if it is a 1, basically you get back the other number. So this is 1110. So then after that there is a shift for the second bit multiplication. So you get 1110. Then this is another shift, but this is all just multiplying by 0, so all are zeros, and then another shift and multiplying by 1, so you are getting 1110. So ultimately you are getting this one as the result. So this way the rules of multiplication, addition, they remain same. Okay. Now for the fractions. Okay, so how are the fractions represented? So just for fun, so you can look into the decimal fractions, like how they are actually, what is the interpretation of these fractional numbers in decimal number system. Like we represent something like 3.14, and then what we do is that we say, if we are trying to assign weight, so we start assigning weight from this least significant position. So this position is 0, this position weight is 0. So after that, after the decimal point, the first one, this weight is -1, the second one weight is -2. So it goes like this. So in case of, for the sake of conversion, so we can say it is 4 into 10 power -2 plus 1 into 10 power -1 plus 3 into 10 power 0. So ultimately you get 3 points. So this is the decimal interpretation of these fractional numbers. So whenever we are converting binary to decimal, So the same thing has to be done, because you can say that for this 1011 part, so this 1, so what is the weight? So if you just write down, so this is the weights are, so this weight is 0, so this is -1, -2, -3 and -4. So this weight is 1. So now the rule is straightforward. So 1 into 2 power minus 4 plus 1 into 2 power minus 3 plus 0 into 2 power minus 2 plus 1 into 2 power minus 1 plus 0 into 2 power 0 plus 1 into 2 power 1. So from right to left, so we just sum them up. So it then after getting the values, so you just take the sum. So the value is 2.6875. So this way you can convert the binary numbers, which is a fractional number, into the corresponding decimal values. For decimal to binary conversion, the rule is just the reverse. So you have to take the two parts separately. So what we do is for this decimal part, for the integer part, so we take it, we convert it separately, and for the fractional part we do it separately. So for this 3, if we are doing it, if we are doing for 3, so 3 is represented as 1 1. 3 is represented as 1 1, and for this 0.14579, so we go on multiplying it by 2. So 0.14759 multiplied by 2, it gives 0.29158. The portion that comes before this decimal point is 0, and then this 0.29158 is again multiplied by 2, so we get 0.58316. Again this value that is getting is 0, and again we are multiplying it by 2, so this is getting 1.16 something. So this is so this value is 1. So the portion that is coming before the fractional point after doing the multiplication is taken into consideration, and this value we go on multiplying. So this is multiplied by 2 again, so you get a 0 here. After that 0.33264 multiplied by 2, so you get 0 point something. Again multiplied by 2, so you get 1 point something. So it is not ending. So after this, so you can continue further. You can continue further, multiply again by 2. So you will get so this before decimal you will get a 0. So this way it can continue. So it is not ending here, but so if it ends at some point of time, if everything becomes 0, so you can stop at that point. Otherwise it can go till infinity. But definitely for computer systems, so there is a finite storage, so you cannot represent infinitely all the bits after the decimal point. So we have to stop at some point of time. So if you say that we will stop after so many bits, so this is 0.001001. So for the portion before decimal point, so you divide by 2. For the portion after decimal point, you multiply by 2. So this 0 that we have got, so it is coming into this 0 is coming into say this 0. Then this 0 is coming into the next 0. This one is coming as the next one. So it comes like this. The successive bits, they will be coming to the binary system like that. So in this way, you can represent fractions in the binary number system. So this is an exercise. So 29.8. So for 29.8, so if you convert 29 into binary, so this is the number. And 0.8, if you go on multiplying by 2, so 0.8 into 2 is 1.6. So you get the 1 here. Now 0.6 that remains, so multiply by 2, so you will get 1.2. So again you will get a 1 here. Now 0.2 is remaining. 0.2 multiplied by 2 is 0.4. So you get a 0 here. That 0.4 multiplied by 2, you will get again 0.8. So that 0 comes here. The 0.8 multiplied by 2, you will get again 1.6. The 1 comes here. So that way it goes on. So this way we can convert these decimal numbers into binary numbers. Now once the decimal number has been converted to binary, so you can do the conversions to other number systems. Like here, so to convert into octal number system, so what we are doing, so we are making groups of 3. So we make a group of these 3 bits, and then we make a group of these 3 bits for the integer part. So this is 35. For the fractional part also we do the grouping, but here grouping starts from this side. Okay, so grouping should start from the left side. So this is one group, this is the next group. So first group is giving me the number digit 6, next digit giving us 3. For hexadecimal, so you take groups of 4. So that is the first one. So for the integer part, you start from the least significant bit position, and here you take two more zeros. So that way you get this part is 1 and this part is 8 plus 4 plus 1, that is 13, which is D. And for this fractional part, you start grouping from this side. So this part we group, these 4 bits, then you take 2 zeros and you group this part. Okay, so this is 8 plus 4, 12, that is C. So you get 1D CC. So this way you can do these conversions. Okay, so you can convert the decimal number to binary number first, and then from there using the conversion rules, so you can go to octal number or hexadecimal numbers.